Right. So I will talk about some recent progress towards the overfull graph conjecture. I will start with some of the basic concepts, and then talk about the restriction of the conjecture on graphs with a small core degree, and then quasi-random graphs, and also on graphs of a large minimum degree. I also listed some open problems at the end. So let's start with some basic concepts. So when we say an edge coloring, we mean an assignment of colors to the edges, so that if two edges they share an endpoint, they should receive distinct colors. So by this definition, a color class, which is defined as a set of edges assigned with the same color, is actually a matching. And when we say edge k coloring, we just take the integers from 1 to k as the colors. So the chromatic index of G is defined as the smallest integer k, so that G has an edge k coloring. So one easy observation is that for any graph, the chromatic index is at least the maximum degree of the graph. So take this example here, you see we have this Peterson graph, and we have an edge for coloring for the Peterson graph. Actually, it is optimal. So this lower bound for the chromatic index is maximum degree. And for all simple graph, Wiesen proved in 1964 that the upper bound is actually delta G plus 1. So from here, we can see that for all simple graphs, its chromatic index is either the maximum degree or maximum degree plus 1. So naturally, we can partition all simple graphs into two classes. Class 1 are those with the chromatic index equals maximum degree, and class 2 are the rest. So although only two classes, but it's proved by Hoyer in 1981 that it's NP complete to determine whether an arbitrary graph is of class 1. As this Peterson graph, as I already mentioned, that this Peterson graph actually is a class 2 graph. We have to color the edges using 4 colors. So the question is like, we have 2 classes for the simple graphs. So the question is like, for which class has more graphs? So there are 143 collected graphs of order at most 6, but among all those graphs, only 8 of them are class 2. All others are class 1 graph. So from here, we probably have a sense that like most graphs are class 1, right? And it is indeed the case proved by Erdős and Wilson in 1977 that almost all graphs are class 1. So in particular, they proved that for the random graph Gn, take the edge possibility to be half, like almost all of them are class 1 graph. So then from here, then one question is like, why do we still study edge coloring? Because like almost all graphs are class 1. Well, because we still want to know what kind of graphs are class 2, right? It's the same thing like in the math history, people were trying to prove the number pi is irrational. So this is what mathematicians do. So for research on edge coloring, we focus on classify if a given graph is class 1 and class 2, and we want to try to characterize some properties for class 2 graphs. And in terms of what causes a graph to be class 2, well, basically, for one of the reasons, it's just don't know what is the reason. So it's kind of like unknown. Like for this Peterson graph here, and the second graph, we call this one P star. This is just obtained from the Peterson graph by deleting one vertex. And for the third graph here, if you observe, if we contract these 3 vertices into a single one, then you see that that's just a P star. And for the last graph here, the same thing, if you contract these 3 vertices into a single one, it's just the P star. There are also like 4 graphs of maximum degree 4, which are class 2, but still you cannot really characterize the cause of the graph to be class 2. But the second reason for graph to be class 2 is simply because the graph has too many edges. Those are the 8 exceptional graphs of order at most 6 that are class 2. So for the first one, you see here, we have actually this first 1 and 2. Those are other cycles of length 3 and 5. For each of them, a maximum for the triangle, a maximum degree, a maximum matrix can only contain 1 edge, but the graph has 3 edges, right? So we have to partition the edges into 3 edge disjoint matrices. So we need use 3 colors. And the same thing for this C5. So basically, the number of edges E here is bigger than 2 times 2, right? So 2 is the maximum degree, and this 2 is the size of a maximum matrix. So we need to use, again, use 3 colors. And the same reason for this graph, right? So the maximum degree is 3, and a maximum matrix can only have size 2, and the number of edges E here is bigger than 3 times 2. So the same thing, we need to use 4 colors, and the same for this graph and this graph. And for the rest of this 3, so basically you can see that for the first one, if we deleting this vertex, and for the second one, if we deleting this, and for the third one, if we deleting this, then you see that the graph has subgraph of the maximum degree, of the same maximum degree, but that contains too many edges. Our focus for this talk will be the second cause for this second cause for graph to be class 2. So let's define what do we mean by graph to have too many edges. So we say this kind of graph are overfull. So if a graph is overfull, if the number of edges is bigger than maximum degree times the order divided by 2 rounded down. From this definition, you easily can see that if a graph is overfull, then it has to have an odd number of vertices. So this is one observation for graph to be overfull. And if we define what is called deficiency for a vertex, which is defined as a maximum degree subtract the degree of this vertex in the graph, we call this is the deficiency of the vertex V in G. And then we have an equivalent definition for graph to be overfull. So if G has an odd order is overfull if and only if the sum of the deficiencies of the vertices is at most delta G minus 2. Some examples of overfull graph, as we mentioned before, all other cycles are overfull, right? And also all regular graphs of odd order, those graphs are overfull. And if we have a regular graph of even order, if you subdivide 1 edge just 1 time, then that graph is also overfull. So as we have seen from this example here, containing a delta G overfull subgraph. So by delta G overfull subgraph just means a subgraph of G which has maximum degree the same as G, and that subgraph is overfull. So we call that a delta G overfull subgraph. So the, containing a delta G overfull subgraph is a sufficient condition for G to be class 2. But this is not a necessary condition because we know that the graph P star obtained from the Peters graph by deleting 1 vertex, which is class 2 but contains no 3 overfull subgraph. So then from this, we may ask a question like, can we have a characterization, like what kind of graphs such that containing a delta G overfull subgraph is both sufficient and necessary condition for the graph to be class 2. And one conjecture in this direction proposed by Chetwood and Hilty in 1986 says that as long as the graph has large maximum degree, so bigger than the order divided by 3, then the graph is class 2 if and only if it contains a delta G overfull subgraph. So for this conjecture, so as we already see, the if direction, this direction is trivial, right? Because if G contains a delta G overfull subgraph, then it is class 2. So the hard part is we assume the graph is class 2. We want to prove that it is also overfull. For this conjecture, this condition, the lower bound on the maximum degree, this is best possible. So as seen by this graph P star. So for P star, it has 9 vertices and the delta equals 3. The graph is a class 2 but contains no 3 overfull subgraph. So this P star serves as a sharpness example, but also is kind of like, at least from my knowledge, it's the only known sharpness example. By some calculation, so when we look for a delta G overfull subgraph, so the subgraph has an odd order. Basically, we take any induced subgraph of G, which has odd order and at least 3. We count like how many edges are in this induced subgraph. So if we do this calculation, we can see that if we have a k-regular graph on 2 n vertices, then the graph contains no k overfull subgraph. If k is at least n, if n is odd, or k at least n minus 1 when n is even, then the graph has no k overfull subgraph. So in other words, if the overfull conjecture is true, then for all such k-regular graph, it should be class 1. So actually, I believe you already recognize this. This is the one factorization conjecture, right? So it is a consequence of the overfull conjecture. And also another, this is also just directly coming from calculation on the edges. So if n is even and the minimum degree is bigger than n over 2, then any delta G overfull subgraph of G has a form of G deleting one vertex. So here this vertex X is one vertex of small minimum degree. So for the overfull conjecture, if it is true, it actually implies a polynomial time algorithm to determine the chromatic index for graphs with maximum degree bigger than its order divided by 3. So because proved by Nielsen in 2001 that for graphs, if the maximum degree is at least n over 3, then it has at most 3 induced delta G overfull subgraph, and it is possible to find one in polynomial time. And if the maximum degree is at least n over 2, then it has at most 1 induced delta G overfull subgraph, and it is possible to find one in linear time. So this is the one big consequence of for the overfull graph to be true. So in that case, the NP complete problem of determining the chromatic index for graphs G with a maximum degree large will be simple. And the overfull conjecture also implies several other conjectures in edge coloring. So to state that, we need these 2 concepts. So the first concept, what do we mean by a graph is delta critical, or simply just says critical. So this just means the graph itself is a class 2 graph. And for any proper subgraph H of G, the chromatic index of H is smaller than the chromatic index of G. And we say a graph is just overfull. That means that if we take off exactly one edge, the graph is overfull. But if we take off exactly one edge, then the graph is not overfull anymore. So that's just overfull. And the overfull conjecture implies the one factorization conjecture. I already mentioned this one before. And also it implies what is called a splitting vertex conjecture. So what this conjecture states is this. So we have a k-regular graph on n vertices. Here k is bigger than n over 3. And the graph is class 1. So it's class 1 regular, of course, n is even here, right? Then we split this vertex, split one vertex of the graph. So by splitting one vertex, it means like this. So suppose we have vertex x. It has like, is incident with some edges. So when we split this vertex like into two, x1 and x2. We will put an edge between these two new vertices. And then for the 4 labels of x, we can just arbitrarily distribute them between x1 and x2. So the degree of x1 and x2 will be required to be at least 2, but we can arbitrarily distribute the neighbors of x as the neighbors of x1 and x2. Easily by computing the edges of this new graph, let's call this G star, you will see that the G star is overfull. So it is a class 2 graph. In order to prove that it is delta critical, it is equivalent to show that if you take off any edge from G star, the remaining graph is no longer class 2 anymore. If the overfull conjecture is true, then use this condition. So we can see that the only reason for G star to be class 2 is to for G star to have a K overfull subgraph. But then just use calculation, you will see that the only K overfull subgraph of G star is G star itself. So this proves that G star not just class 2, it is also delta critical. And the another conjecture is the just overfull conjecture. So this conjecture saying that if G is a graph of order n, and we require that the maximum degree to be at least n over 2, then G is delta critical if and only if G is just overfull. So the implication, if the overfull conjecture is true, then the just overfull conjecture is true. And the implication here is pretty simple to argue that. So suppose we assuming that the graph G is a delta critical, right? So then the graph G is a delta critical is a class 2 graph. So if the overfull conjecture is true, because this condition n over 2 is bigger than n over 3. If the overfull conjecture is true, then G being class 2 implies G contains a delta G overfull subgraph. But G is delta critical. Take off any edge, the graph is not class 2 anymore. That means G itself is overfull. G itself is overfull, then it's also delta critical. So that means just overfull, right? You cannot remove any edge to still keep the remaining graph to be overfull. And on the other hand, suppose the graph is just overfull, then which implies that the graph is class 2. So which implies the graph is class 2. In order to show that it is delta critical, we need to show that every edge is critical, meaning that remove that edge, we will decrease the chromatic index. The graph is just overfull, and we have this degree condition. So we have this degree condition. By this degree condition, you can really calculate this. G is just overfull. That implies the order of G is odd. So with this degree condition and the condition that n is odd, you can see that show that under this case, G is the only possible delta over G subgraph of G, and which consequently implies that G is delta critical. So those are the 3 conjectures which are implied by the overfull conjecture. So and for the overfull conjecture, the progress, we have some partial results on this overfull conjecture. So it was first proved that it is true if the maximum degree is really large, like order subtrend 3, then it is true. And then Planhold, he proved that if the graph has even order n and the minimum degree is big, about square root 7 times n divided by 3, then such graphs satisfy the overfull conjecture. And in 2018, Planhold improved the lower bound on the minimum degree to be 2n/3 by applying this result, the result on the one factorization conjecture. So as we mentioned before, the one factorization conjecture is a special case of the overfull conjecture, and it was proved for large n by this group of mathematicians. And for the other direction, looking at like the minimum degree to have the graph, well, this actually, we are looking for the difference between the maximum degree and the minimum degree to be big. So this is a joint work with Cao, Chen, Jing. We showed that if the difference between the maximum degree and minimum degree is big, and the graph is critical, then such graphs are itself overfull. And for now, I will move on to the restriction of the overfull conjecture graphs with a small core degree. So to this, let's define what is called the core of a graph G. So the core of G is defined as the subgraph induced on its vertices of maximum degree. So like in this example, you can see that the maximum degree of this graph is 4, and we have 3 vertices of maximum degree. And then the subgraph induced on these 3 vertices is a path of order 3. So there are a lot of research on characterizing a graph as a class 1 or class 2 by looking at the core of the graph. So Wiesen in 1965 showed that if the core has at most 2 vertices, then G is a class 1. And Fournier showed that if the core of G is a forest, then G is a class 1. So by the result of Fournier, you see that in order for a graph to be class 2, then the core should contain a cycle, right? Then, so Hilton and Joe proposed the core conjecture. So just saying that if we take a graph, a collected graph with maximum degree at least 3, and the maximum degree of core is at most 2, then G is class 2 if and only if G is overfull, or G equals P star. So here P star is a Peterson graph obtained by deleting one vertex, if you recall. So if you look at this restriction on the core, so maximum degree of core is at most 2, then we see that the core actually consists of cycles and paths, right? Vertex disjoint cycles and paths. Actually, if we require the graph, if we assume in the graph, such graph to be class 2, then you can easily prove that in that case, the core is nothing, just those vertex disjoint cycles. So if this one consequence of this core conjecture is, if this core conjecture is true, then for collected graphs G with maximum of the core degree at most 2, then we can easily determine the chromatic index of G by just counting the number of edges if G is not P star. So in other words, we are just determine if the graph G is overfull or not. So to easier state, we will call what is called a Hilton-Joe graph, so HZ graph, which is defined as a collected class 2 graph with the maximum degree of its core to be at most 2. And the first breakthrough of the core conjecture was obtained in 2003. That showed that this P star is the only Hilton-Joe graph when delta equals 3. And an alternative proof for this delta equals 3 case was also given in 2007. And the next case for delta equals 4 was obtained by Christian and Raber in 2017. And they show that the only HZ graph looks like this, which is obtained from K5 by deleting one edge. And also, if you observe a little bit from here, we will see that this red part, this is the core of the graph, right? So that's a cycle, C3. And the rest of two vertices, each of them, the maximum degree of the graph is 4, and the rest of two vertices, they have degree 2. And between the core and the rest of two vertices, we have a complete bipartite graph between them. And recently, joint work with Cao, Chen, and Jing, we showed that the core conjecture is true for all delta at least 4. Again, so the if direction for the proof is trivial, because if G is over 4, we know that's class 2. So the proof is really focused on assuming we have a graph, class 2 graph G, such that the maximum degree of core is at most 2. We want to show that it is overfull. And for such a graph, there is a characterization. It's just a little bit of structure characterization. So for such a graph, by apply Wiesen's adjacent lemma, it's quite easy. So I will not show the work, but if any of you familiar with Wiesen's adjacent lemma, it's really easy to prove. So for such graphs, they are delta critical. So we have a class 2 graph, which has the collected class 2 graph, the maximum degree of its core is at most 2. For such graph, they are actually delta critical. And the core is 2 regular, so just the vertex disjoint cycles. And the mean, if the delta equals 2, then it's just odd cycle, nothing else. But otherwise, the minimum degree of the graph is delta minus 1. So in the graph, we only have 2 values for degrees, delta minus 1. And every vertex of G has at least 2 neighbors in the core. So has 2 neighbors of degree delta. And what we actually proved was we proved an equivalent conjecture of the core conjecture. So this equivalent form was given in the book by those authors, the edge coloring, Wiesen's theorem, and Goldberg's conjecture. In that edge coloring book, it has this equivalent form of the core conjecture.
Mama, I told my piano, I mean my little shirt about the piano.
Okay, may I finish the talking?
Okay.
So the equivalent form is saying that for if we take an HZ graph with maximum degree delta, then either G belongs to this class called O delta, or when delta equals 2, the graph G is just an odd cycle. And when delta is 3, then G is P star. P star is a Peterson graph. So since we were only considering delta at least 4, so we will just need to prove that if we have HZ graph with maximum degree at least 4, then G belongs to this class. And this class basically constructed in this way. So you see on the top, we have a 2 regular graph on N1 vertices. It's just a bunch of cycles. And on the bottom, we have a delta minus N1 regular graph, which has order delta minus 2. And in between, we have all the possible edges. It's join. And we require that this number N1 to be at least 3 at most delta minus 1. And we also require N1 plus delta minus 2, which is the same thing as N1 plus delta, to be odd, because we want this graph to be overfull, right? It has an odd order. So by this construction, you see that all the vertices on the top, those are the maximum degree vertices. And all the vertices on the bottom, those have degree delta minus 1. So to prove that any Hilton Joule graph with delta at least 4 belongs to this class, one of the foundation steps is to show that if we take any 2 adjacent delta vertices, then they have exactly the same delta minus 1 neighbors. Delta minus 1 neighbors means neighbors of degree delta minus 1. So locally, if we take a vertex of maximum degree here, R, and it has exactly two neighbors of degree delta. So U and V, those two vertices are of degree delta. And all the remaining vertices, remaining neighbors of R, S1 up to S delta minus 2, each of them has a degree delta minus 1. And if you recall, we want to show that such graph is overfull. So if such graph is overfull, you look at the deficiency. So each of these vertices has a deficiency 1, right? Because the degree is delta minus 1. And all those vertices together, the deficiency is already delta minus 2. So, and we said a graph is odd order is overfull if and only if the deficiency is at most delta minus 2. So here it's delta minus 2. So that's exactly. So basically, what we need to prove is that we need to show that in this entire graph, all those vertices S1 up to S delta minus 2, those are only small degree vertices, and everything else they have degree delta. So to prove this, actually some of the intuition, as we said, is like we take this vertex R, this vertex R, this is a maximum degree vertex, and we take U, it's a maximum degree vertex. We will assuming that R and U, they don't have the same delta minus 1 neighbors. So basically, U, we will have a neighbor X, which has a degree delta minus 1, but X is not a delta minus 1 neighbor of R. The intuition is kind of like, suppose if this vertex U has mainly delta minus 1 neighbors other than the delta minus 1 neighbors of R, then you see that the deficiency for this graph will be big, right? In this case, actually, it's easier to get a contradiction. So then the thing is, how are we going to argue that this vertex U has mainly delta minus 1 neighbors outside the neighborhood of R? For the work of Christian and Rembrandt for delta equals 5 case, they kind of just enumerate all the possibilities. But for us, because delta can be anything, we cannot enumerate everything. So what we did was we show that we have two kind of breakthrough work. The first is to show that as long as we have, we can show U has 3 small neighbors outside the neighborhood of R, we can already find a contradiction. And then how do we get these 3? Basically, we use the idea of combine the idea of Vision fan and kill state path. So the graph is critical. We can delete this one edge, color the rest of the graph using delta colors. So we assuming the color missing at R is 1, and the color missing at S1. So it has 2 missing colors, 2 and delta. And we can, by choosing an appropriate uncolored edge, we can assuming that also renabling the vertices and colors. So assuming the color missing here is 2, and this one is 3, and 3, this is 4, and this is alpha, and here is alpha plus 1. And by some argument, we can assuming the edge of RU is colored by alpha plus 1, and the color missing at X is alpha plus 1. And we showed that for the color for this edge UX, for this edge, this color has to be some color missed in the multi-fan. And if this color is all the possible colors in the multi-fan, we have 2 sequences, right? It's either the color delta or the color started from 2, like it's induced by the color 2, because we have 2, 2, 3, 3, 2, 4, etc. like this. So if this is a color delta, then we can show that like this vertex U is not going to be adjacent to the first vertex, not going to be adjacent to the last vertex. And if this color is something else, for example, like 3, then we can show that U is not adjacent to S2 and or S3. And with this argument, which gives us like more small degree neighbors of U outside the neighborhood of R, and which helps us to finish the proof. And with this proof, So we can prove that all such Hilton-Joule graph belongs to this class. And something we can observe is this number of vertices n1, which is at most delta minus 1, right? And we have on the bottom, we have at most delta minus 2 vertices. So from here, you see that delta is bigger than n over 2 plus 1. And for also, we know that all such graphs, they are delta critical. So this is those two are conditions. Once we prove the Hilton conjecture, we know the graphs have this property. So, and as a generalization, we also proved that as long as we have a delta critical graph, which has maximum degree bigger than half n plus 1, and the minimum degree of the core is at most 2, then the graph is class 2, also implies that the graph is overfull. Okay, so this is the part for the excuse me, overfull conjecture on graphs with a small core degree. So next, I will move on this to the restriction of the conjecture on dense quasi-random graph. So for quasi-random graph, it has many equivalent definitions. If you look at this on the wiki, you will see that we have this many different definition in terms of discrepancy or subgraph counting, etc. But here we will use this definition of one-sided version of epsilon regularity. So we take two real numbers epsilon and p bigger than 0 and less than 1. We call graph G on n vertices is lower p epsilon regular if for any disjoint subset ST, each of size and at least epsilon n, the number of edges between S and T is at least P minus epsilon times the size of S times T. So you can compare this with like the number of edges between kind of like a G and P or something, right? So in that case, it's like P times size of S times T. So here, instead we have P minus epsilon. So Glock, Kohn, and authors in 2016, they proved that give you a lower P epsilon regular graph on n vertices, and here n is sufficiently large, then we can, as long as the difference between the maximum degree and the minimum degree is small, then the graph is class 1 if and only if it contains no delta G overflow subgraph. So, but it requires n to be even. So in other words, the overflow conjecture is true for such class of graphs. And they also show that you can find a polynomial time algorithm to find an optimal coloring. And they conjecture that the same result should hold for such quasi-random graph with odd order n. And I proved their conjecture. And also, but here, the statement is a little bit different. Instead of say G has no delta G overfull subgraph, we just have if and only if G is not overfull. And also we can find a polynomial time algorithm to give an optimal coloring. So the reason of we have this simpler statement here is because for such graphs, it has an odd order. The only possible delta G overfull subgraph is just the graph itself. And lastly, I want to look at the restriction of the overfull conjecture on graphs of large minimum degree. So let's recall the one factorization conjecture and the result proof for large graph here again. So the degree here is about n over 2, and the graph is required to be k regular, and n is right, and n is even. And then also such graphs are class 1. So as a asymptotic generalization, so with my colleague Planthold, we showed that for even n, well, we just assume the graph has 2n vertices, and the minimum degree. So instead of saying the graph to be regular, we require the minimum degree of the graph to be about 1 plus epsilon n. So epsilon n above the half of the vertices. Then G is class 1 if and only if it contains no delta G overfull subgraph. And then also the same thing, we can find a polynomial time algorithm that finds an optimal coloring. So let me mention a little bit the proof idea for this, the last two results on the quadrirandom graph and on this graph with large minimum degree. So for the quadrirandom graph case, we have the graph G, which has an odd order. So basically what we do is we will add a vertex to the graph to make a new graph called this G star, such that the degree of X, well, I should say the degree of X in G star, which has a minimum degree of G. So by this restriction, then we can, if we assuming the graph G has no overfull subgraph, then the new graph G star also have no overfull subgraph. Then as for this quasi-random graph, the difference between the maximum degree and minimum degree is small. So basically we can take off some linear forests from the graph to reduce a regular graph. So once we get a regular graph, then the process is we will have a random partition of the vertices into two parts, like here, A and B. And such that for every vertex in its own part, the degree of this vertex in its own part is approximately the same thing as the degree of this vertex in the other part. Then for this graph, then we just kind of to concretely give a coloring. So basically, we will first to color all the edges, in A, all the edges in B, together with only a few edges between A and B, such that for this coloring, such that every color class is the perfect matching. Then after that, what we will be left with is we have a regular bipartite graph, which is always class 2. Then you combine the two colorings together, that gives a delta G coloring of the original graph. And for the second part for the proof is kind of similar. So in one of the case, when delta G, the difference between delta G for this result and the delta G is small, we can reduce the graph to to a regular graph after taking some linear forests. And then we apply this same process. So when the difference between this is big, we do the same. So we will do this kind of partition. But in this case, we are not started with a regular graph. But we use the condition that this condition is big. And also when the number, so let me call this V of delta, the set of the minimum degree vertices. If that is small, we can reduce that to a simpler case. If this is big, then we cannot really use these two things as some middle procedure to help deal with the non-regular case to get a concrete coloring in this process. And finally, I have some open problem here. So the first one is recall for the overfull conjecture in terms of only considering the maximum degree. It only proved for delta G when delta G equals n minus 3. So then the question is, can we prove this for n equals 4? And when in terms of restricting the graph to have a large minimum degree, so can we show that if the minimum degree is about n over 2, and when n is even and large, can we show that such graph satisfies the overfull conjecture? So if we can prove this, then it's actually, in some sense, actually it generalizes the work on the one factorization conjecture, because we require here only asking minimal degree instead of saying the graph to be regular. This will be everything I have. Thank you very much for your attention.